homework 5 part B. So this one we need to using the momentum balance equation and energy balance, assuming negligible friction derived Betz's law for the maximum power that can be extracted from air of a given density velocity passing through a turbine of cross-sectional area S and constant average axial velocity. What is the optimal ratio of the outlet air velocity to the inlet air velocity? Okay. So first we're going to start with this equation. So P is equal to rho SV times V1 minus V2 times V. And then what we do with this, we simplify this, we get P is equal to rho SV times V1 squared over 2 minus V2 squared over 2. Then we can keep going. Rho S times V1 minus V2 times V2 squared is equal to rho SV over 2. This is rho. Rho is V over 2 times V1 squared minus V2 squared. Okay, so what we can do is we can cross out this, and we get V1 minus V2 times V is equal to V1 minus V2 V1 plus V2, and all of that is over 2. So we cross out this, and this, and we get V is equal to V1 plus V2 over 2. Okay, so now we can go back up here. We're going to change this into P is equal to 1/2 rho S. Change this into V1 plus V2 over 2. Those parentheses times V1 squared minus V2 squared. So we're going to keep simplifying this. So P is equal to 1 over 4 rho S times V1 plus V2 times V1 squared minus V2 squared. Okay. So I'm just going to FOIL this out. So you get V1 cubed minus or plus V2 times V1 squared minus V1 times V2 squared, and minus V2 cubed. Okay, so now we're gonna simplify this by taking V1 out. So then, yeah, 1/4 rho S times V1 cubed. So let me get 1 plus V2 over V1 minus V2 squared minus V1 squared, and then minus V2 cubed over V1 cubed. All right, so now what we can do is we can simplify this, and we're gonna say that R is equal to V2 over V1. Now that's it. What that's gonna do is it's gonna help us simplify these terms into an easier thing like R. So go right here. P is equal to 1/4 rho S V1 cubed times 1 plus R minus R squared minus R cubed. And so what we're gonna do is we're gonna take the derivative of this, so dP over dr. So then what this is gonna give us is just 1 plus R, and then 1 minus 3R equals 0. And then from this we get that P optimal equals 1/3. Okay, so now we have P optimal, so I'm going to erase these terms down here. Okay, so now we have P optimal equals 1/4 rho S V1 cubed. Then we can so if we find we can plug this term in for R, so then we get 1 plus 1/3 minus 1/9 minus 1/27. So now we're gonna do is we're gonna divide this by 27, get like terms, and what we end up with is P optimal is equal to 16/27 rho S V1 cubed, and that's a final optimal value.